We're going to do another liquid-liquid extraction problem. So in this problem we have 500 kilograms per hour of a feed that is 30% pyridine and 70% water, and this is going to be extracted with pure chlorobenzene. Now we have the equilibrium data here, and for the first part, a single mix receptor is used, and what this means is essentially we're using a single stage operation. We also have the chlorobenzene flow rate. So before we get started, let's first write out all the stream information that we know. So we have the feed, and then we have the extract, and the extract is chlorobenzene, and then the flow rate here is 500 kilograms per hour, and the extract is 300 kilograms. Now for the composition, we have water, pyridine, and then chlorobenzene. Okay. And so we know that initially the feed is 70% water, 30% pyridine, and 0% chlorobenzene, and the extract is completely chlorobenzene. So far so good. The next step is to create the equilibrium diagram. Since this is a liquid-liquid extraction and all liquids are miscible with each other, we're going to have to use a ternary phase diagram. And the way we create this is by first taking the equilibrium data, and then we need to plot one specific element on one specific axis. So in this case, we're going to choose water as the x-axis and pyridine as the y-axis. So we're going to start by creating a scatter plot, and then when we select the data, we're going to add first a series for the extract, and then the x-axis is going to be water, and the y-axis is going to be pyridine, like so. And then the second series is going to be the raffinate. The x-axis is going to be water once again, and the y-axis is going to be pyridine. And so, as you can see, we get this nice phase envelope here. And let's just go ahead and trace some lines so that we can clearly see the delimitations. There we go. Now, this gives us the phase envelope, but it still doesn't give us the equilibrium relationship. To get the equilibrium relationship, we need to draw the tie lines. The tie lines are actually quite simple, so you simply need to connect the dots. So the way this equilibrium graph is set up, this line, this row, is in equilibrium with this row. And this essentially means that you just need to draw lines like that. And so let's go ahead and do that. Okay, so now we have the tie lines drawn. The next step here is to determine the mixing point based off of the flow information of the feed and the extract. So as you may recall, the mixing point is simply the composition you would get if you were to take the feed and the extract streams, the inlet feed and the extract streams, and just mix them together. Hence the name mixing point. So the flow rate of the mixing stream would hypothetically just be the two streams added together, and then the composition of the stream would be equal to 500 times the amount of water divided by the total flow rate, and we would get this. And then we can repeat this calculation for all of the components. So pyridine, chlorobenzene as well. And there we have it. So now what we can do is we can take this and then we can plot it on our graph. And if this is correctly calculated, they should form a straight line. So all these points should be collinear. So once again, let's plot the water. And the purity. And as we can see, this is collinear, so this we've correctly calculated, and we can see that the mixing point is here. So it falls in between two tie lines. Okay, to me, this looks like the water for the extract is approximately 1.4%, so 0.014. And it looks to me that the pyridine, or the Y component here, is about 0.221. And for the raffinate, I would say this is about 84% water. And then for the pyridine, it would be about 0.159, slightly below the 0.16 mark. So the flow rate we do not know, and we'll have to calculate it. But first we can calculate the chlorobenzene concentration. Now, to calculate the flow rate, we're going to have to conduct a mass balance. So as you can see here, the typical component mass balance and the overall mass balance mean that the raffinate and the extract stream need to add up to the mixing point, so they need to add up to 800, and then the individual component as well needs to add up to this times whatever component it happens to be. So by manipulating this, we simply get that R is equal to Zm minus Xm divided by the raffinate and extract compositions, the difference between the raffinate and extract compositions. So let's do that. So this is going to be equal to, and let's just take an arbitrary component. So let's take water. It's going to be equal to water times this minus the extract composition times 800 divided by the raffinate composition minus the extract composition. And this gives us a value of 410.6. And the extract composition is obviously just 800 minus this. And there we have it. That is our flow rate for the extract and raffinate. For the second part of this question, we need to take the raffinate from the first stage and then set it into a new stage. So we effectively have a two-stage system, but it is cross-flow. So we essentially just solve this the exact same way otherwise. So let's start by drawing out the second mixing point. And so this is going to be the combination of the raffinate stream and then a new chlorobenzene stream. So let's just add a new extract stream. So this would have a flow rate of 300 kilomoles per hour and then just be pure chlorobenzene. And so the mixing stage, the mixing stream, is going to be equal to this plus this, and then the composition is going to be equal to 84% water times the flow rate of the raffinate divided by the total flow rate, and then for pyridine it is the same thing. And then finally, for the chlorobenzene, it is going to be 300 kilomoles of chlorobenzene, so it's going to be this times this divided by the total flow rate. And there you have it. So that is the second mixing point. So what we're going to do is we're going to plot this, and if it is correctly calculated, then it should also be collinear. So let's go ahead and do that. And once again, remember to keep your axis consistent. So because we're using water as the x-axis, we need to keep using that. And there you go. And since this was correctly calculated, you can see that the points are collinear. And we can see that the mixing point is now here. So let's draw a new line. So you can see that it approximately goes from here to here. There we go. And now we simply need to find the compositions of the new streams. So now, if we look closely, we can guesstimate where the compositions are. Obviously, this is a graphical solution, so we can't be super precise. But to me, it looks like this is about 0.8% water and 13% pyridine. And remember, because this is the extract, we're looking at this side, and for the raffinate, we're looking at this side. And then for the raffinate, I would say this is about 94% water. And for the pyridine, I'd say this is about 6%. So for chlorobenzene, for the raffinate, it's about very close to 0% chlorobenzene, and for the extract, this would be equal to 1 minus this. Okay, so once again, to calculate the flow rate, we'll use the exact same equation as before. So it is going to be equal to this times this minus this times the flow rate of the mixing point divided by the difference in composition. So it would be this minus this. And there we go. And so obviously the extract is going to be equal to 710 minus the raffinate flow rate. And there you have it. So now we have two streams, and as we can see, this final stream is 94% water as opposed to the initial feed, which was 70% water, which means that we're indeed effectively extracting the pyridine out of the solution. And that is it.